Unless you want to. I'm so pissed.
All right. To start with, I'm going to R all of this in just a minute, but your first step here, when you have H3O plus, should have been protonation of your negatively charged oxygen. We all good? All right, good. So now we're going to call all of this R to make this simpler. So this is what we're looking at, right? This is called a cheat. You like it? Okay. She is cheating already. All right, so here we go. First step is
Chemistry hacks.
protonation of your oxygen here. Doesn't matter which one, right? Second step is loss of the leaving group. You shouldn't have any SN2S sort of concepts in here where you attack the water and push out the leaving group. That doesn't exist, right? These need to be sort of SN1-like, where you form carbocations first, and then, right, it gets kicked out. That's supposed to be O, sorry. So I have a positive charge here now. Third step is going to be the attack of water, right? That's going to come in right here. So now we have this guy, water on, need to deprotonate. I think we've used up enough for it. I think we can go back now. So we have deprotonation as the next step. Now we have protonation of the other oxygen here. Loss of the group. There's a resonance structure. What's so funny?
You're writing really fast. Like a speed.
And finally, deprotonation. Who's able to keep up with me? All right! That's the way to be. Okay. Now this is an impressive board, right? This is what they show when they like scan the science classrooms in all the movies, right? Something crazy on the board like this. I personally think physics is more interesting, you know, with all the little arcs and the, yeah, anyway. Moving on. This is the mechanism. Now, might be a good idea if you have a camera phone to get out and take a picture. That might be faster, right? Yeah, just do that fast. Yeah, Harrison did that. I saw you do that the other day. That was really good. He's like, I'm not writing all this down. I'm waiting for it. Oh, she's done. All right. I should do like my daughter on Snapchat. Like, what is this? What is that? What is that? I don't even know. Yeah. Or my favorite and the stupidest one is. Why do I want pictures like that? Yeah, I know.
Hey, Dr. Dixon.
I do all the craziest things.
I'm recording you, by the way.
I know. Okay. Julia, don't do this anymore. I'll show her this video. Okay. Are there questions about this mechanism? How do we do? Let me just highlight some of the areas where trouble, like, sort of happens. Okay. First and foremost, this is the one that I noted, right? And this is true at every occasion. When you have a good leaving group, something that's protonated and can leave, it leaves before something else attacks, okay? So make sure that you're showing that. As in, the water's not going to come and attack here at this site and push this out, right? Because that's an SN2-like concept, and it's way too crowded in order for it to do that. So we know that it proceeds through these intermediates. Another thing is knowing when to stop. Like, some of you might have gone beyond, you knew what you were going back to, but the trouble is sometimes when there's an open-ended question, you sort of don't know where to stop, okay? So for instance, okay, you knew you were gunning for an aldehyde there, which I think makes it a little easier. But what if you had something like this? And I gave this to you on a test. Okay, let's try and work through this one. What's going to happen here? First of all, always track what you have initially. What is this? name it generically. Don't, it's not like 3-isopropoxy, 3-pentanol or whatever. What is it called? I'll give you some choices. Ketal, acetal, hemiketal, hemiacetal. It's a hemiketal, right? It's a hemiketal. And I know that if I take a hemiketal and I put in water and some acid, I'm going to get back to a... No, going forward would get me to a ketal, right? I can move forward to get to a ketal, right? I can add like CH3OH and some acid, and I can create a ketal. That's for sure, but a ketal would be 2 ether linkages off the same carbon, right? That's not what I have. I have 1 alcohol and 1 ether, 1 alcohol and 1 ether. So going forward would get me to the ketal. Adding water and acid gets me back to the ketone, right? So you need to know where to stop, okay? So as we work through this, and I will work through this one just so we can see it, make sure you know where to stop, because when you have an end product, everyone's good. But when the end product is sort of open-ended, you don't create an end product in your mind that you're gunning for, okay? So immediately when I see this, and I know this is a hemiketal, I know this is what's been added, I know what I'm after. I'm after 3-pentanone. Does everyone see that I've just covered up the ether linkage, and I know this OH is where the carbonyl is. So I know I'm after 3-pentanone, okay? So how do you get to 3-pentanone? You first show now protonation of the oxygen species. You don't need to write all this down. I'm just using it as an academic exercise here. Different than the student number academic exercise. Loss of a leaving group. And this is where we run into trouble. You have this, right? And so sometimes people want to add water in here, right? You're like, oh, I have a carbocation, something needs to add in here, right? But if you stopped and looked at the resonance structure, you would see that the resonance structure is exactly a ketone or aldehyde, in this case a ketone, and you know this is your stopping point, okay? Does everyone understand what I mean? That if you didn't know what your end product was, you would all say, oh, water comes in here and creating a diol, a geminal diol. Yes? But we're going for the ketone. All right. Are there any questions about anything that's on the board? Yes?
On the 4th step.
Count. 1, 2, 3, 4. This step?
No. Yeah, isn't there a resonance?
Isn't that the 3rd step? We're moving on. Maybe it's the 4th structure. It's the 4th structure, yes. This does have a resonance form. This does have a resonance form. You can see that I have not, -1 Dr. Dixon, on an exam, absolutely, yep, this is why I never got 100%. There should be a resonance structure here. I didn't draw that resonance structure, I attacked right here, okay? It's almost like in my mind I know when I'm supposed to resonate to know, I know, and that's frustrating, but I do. Good catch. Okay, are there other questions? Okay, great. So I'm going to erase the board, and today we're going to talk about nitrogen nucleophiles. So we're going to move on and talk about nitrogen. Is that exciting? I used to have an organics professor who used to write like this. He used to be like, and so you create an acetal. For some reason, I'm reminding myself of that when I'm erasing. But you could have taken a picture of all this before. Not with Dr. Kuna. He probably isn't with us anymore. He's like 90 when he taught me. Okay. Okay. So we're going to move into nitrogen nucleophiles here.
Yay.
So this is the use of amines and how they're going to react correspondingly with carbonyl centers of ketones and aldehydes. There are three sort of types of amines. There are primary amines, so there are secondary amines. This doesn't have to be the same R group. Okay? There are tertiary amines. Okay? Remember, amines are classified by how many R groups are attached to the nitrogen. So one R group attached to the nitrogen means it's a primary amine. 2 R groups means it's secondary. 3 R groups means it is tertiary. Okay? Tertiary amines cannot react with ketones and aldehydes. You should really, and I'll point out, but you should understand conceptually why tertiary amines do not react. That is a very conceptual question that has been tested in prior terms in this class. So it is a potential test question. Okay? Primary and secondary amines do react. Okay? But they give us different products with different names. Okay? If I use a primary amine, what I get in the end is an imine. So I-M-I-N-E. If I use a secondary amine in my initial reaction, I get an enamine. Okay? So this is the language that we use. Is that like enema? Yeah, like chemies, it's all related. So this is what we're going to be looking toward today. As always, these aren't great nucleophiles, right? On their own, they're not fantastic nucleophiles. Their conjugate acids got a pKa of 9, so they're moderate. They're not fantastic. And in order to get water off the molecule eventually, I need acid conditions anyway. So these reactions are always run in acid. Now, the trouble with running acid, or running these reactions in acid with amines, is that amines are somewhat basic, as you know. So there is a pH optimum at which all of these reactions will work. Every reaction has a unique pH optimum, okay? So you can never run them truthfully in strong acid conditions, like down at pH 1 or 2, because there, the nitrogen is always protonated, right? If I'm down at pH 1, my primary amine really is going to be like this, and this means that it has no electron pair, and truthfully no ability to serve as a nucleophile, right? And if I'm trying to do a substitution here, or an addition, right, something that I'm trying to move on to an electrophilic center, I need that nitrogen to be nucleophilic. That is really what it should behave as in these reactions. So I have to be careful at the pH at which I run these reactions. You're never going to be probed to what pH is the optimum pH for a given reaction, but you should have knowledge that they shouldn't be run in strong acid conditions and have knowledge as to why that is. Again, the reason is that they become protonated. When they're protonated in their protonated form, they no longer serve as a nucleophile, which is indeed how they're supposed to behave. Okay? So one of the first things you need to do if you want to form an amine or an enamine is to know the pH profile of the reaction, which is one of the very first things you do before you set about setting up any given reaction. Okay? So since we're not in the lab setting and we don't necessarily need to worry about the setup as much, we're just going to talk about these reactions as if they'll run without considering what necessarily their pH optimum is. Okay? So let's run these one by one. We'll start with the imine and then we'll work to the enamine here. So in terms of the imine, I can take a ketone, right, and react it with this primary amine with some acid catalyst, okay? Remember, we want to use something like H2SO4, H3PO4, but we have to be careful. We're probably going to buffer it to some extent, right, so we can stay in a pH realm. In this case, first step always, protonation of?
Carbonyl center.
Of the carbonyl oxygen, right? You're always going to get steps if you do that. Remember, that's always for points, not steps. It's always the first step here. Okay, that doesn't look like a double bond still. There we go. All right, second step. Because there's resonance formed here, right? So second going to do the attacking? The nucleophile. And the nucleophile is my amine, right? So we see attack here at the carbonyl center. Okay. So now I have something like this. Everyone with me? Why did I use a reversible arrow here?
Because it's reversible.
Because it's reversible. That is right! Why is it reversible?
Neutral nucleophile?
Because it's a neutral nucleophile. That's exactly right. You sound like my 12-year-old. Okay, this is absolutely true. It is a neutral nucleophile. And when a neutral nucleophile attacks, it can go on, it can go off, it can go on, it can go off. My phone is currently ringing. Who wants to bet that it's my mother?
It's what?
Her
daughter.
Oh, it's my mother! Yeah, you should. You should be like Mimi. I'm in class. That's actually what she's listed in my phone. And that is her name, M-I-M-I, Mimi. She was supposed to be Herman. She's Hermine instead, though. How terrible is that? She came out as a girl and they named her Hermine. She's had the last laugh, though. She's going to live till she's 100. So, okay. I know, what is she talking about? Maybe this video should go.
I'll edit that part out.
Yeah, you edit that part out. That's good. Okay. My mother doesn't know how to watch the video. So. Let's just pause. A neutral nucleophile. You're absolutely right. Anytime a neutral nucleophile adds, it can go on, it can go off, it can go on, it can go off. So here we go. We're at a reversibility here. What has to happen next? I added a neutral nucleophile. What's the very next step? Deprotonation. This got to come like immediately. Deprotonation. Amen. That's right. Here we go. So now we have this piece here. Now, oops. What's going to happen next? I'm in acidic conditions. What could potentially happen? Because I can certainly stop here, right? This is not the end product, though, I'll tell you. This is not it. This is not the end of the story. So, what can we consider as another potential pathway? You can protonate the oxygen. That's exactly right. And that can go on, and that can go off, and that can go on, and that can go off. So that's absolutely right. Here, right? Okay. Now what do I have? I have a good leading group. Now this is something you can do, and it saves you steps. Okay? You can kick it out. Okay? Does everyone see what I've done? I've kicked out the leaving group. So now I have this in the end. And there's one last step here. What is it? Deprotonation. Okay. So that's absolutely right. And here is the end of the line. So this is an imine. That's what we form down here. Okay? So, imines always have the generic formula, okay, that is like this. You always form, in the end, a double bond, instead of to the oxygen, to the nitrogen of the primary amine. Now, I had two protons that were lost through the course of this reaction, right? The first proton on the amine that was lost was here. What was the purpose of deprotonation here?
Restore the...
What?
Thinking out loud.
Thinking out loud, that's okay. Thinking out loud is good. What's the purpose? Why do I deprotonate these neutral nucleophiles?
So we can get that lone pair.
Not because we make the double bond, but it allows this bond to stick, right? This bond here can't stick, can't stay, unless this nitrogen is deprotonated. Because otherwise, this is going on, this is going off, this is going on, this is going off, right? It's not going to stay attached to your molecule until this is deprotonated. react. Okay? Because with the tertiary amine, if we follow through just with a generic one here, and I had this guy here, and I added a tertiary amine, right? This is what I get. There is no hydrogen that can be removed that allows this bond to stick, right? So it absolutely situates itself reactant center. It sits toward the reactant side because it can go on, off, on, off, on, off, right? Off is better because it's neutral. So this is the very step that explains, right, why a tertiary amine can't be used. So a primary amine and a secondary amine have at least that hydrogen, right? They allow the nitrogen to add, the bond to stay. Our second hydrogen was lost out here, right? And that was to allow the imine to form. Note the structure of an imine again. It's the carbonyl carbon double bonded to the nitrogen of the primary amine. Okay? What we're going to see with an enamine is a difference out here, which we're going to compare in a minute. Are there questions about this imine formation? No. Okay. So let's show the formation of the enamine. Let's take the same material. Use that guy up there. Of the carbonyl. I shouldn't have even erased that. I would have saved myself some time. Second step, these always follow one by one. Attack of the nucleophile. My nucleophile here is my secondary amine. Here the bond can stick, right? I said secondary amines can add. Absolutely. Because this nitrogen that just did the addition, that just served as the nucleophile, does have a proton that can be released, allowing this bond to stick, in essence. So the bond is on there. The next step is, as before, protonation of the oxygen, right? If I protonate the nitrogen, I'm moving backwards. I'm moving in reverse. I'm trying to find something new and novel. So I have protonation of the oxygen here. And that nitrogen still has electron pairs to do the same thing, right? To help aid the leaving group to leave, which it certainly can do. It can kick down and push out the leaving group. And this is what I get when all is said and done here, is I have this. Now this cannot be the end of the line, okay? This cannot be the end of the line, but I can't deprotonate that nitrogen, right? Not like over here, right, where I could deprotonate the nitrogen. I cannot do that. There's no hydrogen on that nitrogen for deprotonation. So this is where we see a difference. Now, you should note that there are two potential, what I would say, alpha sites. I'm using this language again. I used it last class. Those are the sites directly next to the carbonyl site, right? That nitrogen is attached to what was once the carbonyl site. There are two alpha sites, one on the right and one on the left. You are all so used to making the more substituted alkene that you always pick the more substituted site. Enamines don't work that way. Enamines always form the double bond toward the less substituted carbon, which means This is a no. I cannot show the same mechanism by pulling this hydrogen, the one I'm about to show. You must always use the one from the less substituted side. So this is actually a nice, quick, little ditty to work with. So in this case, then, I pull this hydrogen here, and this is kind of like, although nothing's leaving, it's kind of like an E1, right? I pull this hydrogen, it leaves behind electron pairs. They flow toward the positive charge, and as these pi electrons move up, that positive charge is satisfied because an electron pair comes up to reside on nitrogen, and nitrogen is now neutral, right? It's a neutral molecule. Oops. And hence, in the end, I get this form. And this is what makes it an enamine, okay? It's a nitrogen attached to where the carbonyl carbon was. With a double bond on one side, okay? Does everyone see the difference between an enamine, the left side of my double vertical line, and an imine, right? So this is the structure of an enamine, okay? Yeah?
Just to recap, you said it was the less substituted side of the alpha carbon?
Yep. It's a less substituted alpha carbon. So way back when we started with these ketones and aldehydes, this guy has two alpha carbons, alpha and alpha. So there's two alpha sites. Those are always the ones that flank the carbonyl carbon. My point is you'll always pull from the less substituted alpha carbon when you're forming your enamine in the end. Yes? It pulls from the less substituted. It has something to do with the transition state here between like sort of the steric hindrance that exists, that abounds here in the transition state along the path. And that is why. It's actually a steric hindrance argument. People love to use that as an argument for reactivity. Here is a place that it's actually true. Okay? I know. What's going on, right? Oh, that's my son now. It's a half day, isn't it? Today's a half day. What time is it?
12:30.
12:30. Okay. Yeah, it's a half day. I'm not going to answer that, though. So we're just going to listen to it. Okay. Are there questions about this mechanism? All right, so the question is, what do I do with imines and enamines, right? That's really a good question. Like, why do I care? That'd be a good question, right? Why do I care to form either of these? Okay, so let's talk about the utility. Let's first make sure that we could, without working mechanistically, because we're not going to go through the mechanisms in the forward direction again, because that gets a little dull. Without working through the mechanisms, see if we can't draw the products for these reactions. Okay? So I'm going to put up a couple, and you're going to draw up the products here. So work with that here. Bless you.
Thank you.
right, so from this first one, should be able to show this as your product. How'd we do? We did good? Okay, so one thing you can do with this, working forward, and I'm kind of cheating, I'm using H2 platinum, and you actually can use H2 platinum here. You probably have to change the pressure or temperature conditions, I'm sure, in order to get this reaction to go. I don't think regular old H2 platinum, as with an normal alkene, would work per se, but this actually then will reduce the double bonds, and I'm just going to move that along. I hope that's okay with you. Move that just down here. And actually now, in reduction of the double bond, creates an amine for us, right? This is what we call reductive amination. That's what we call it, reductive, because the last step is the reduction step. Animation, because I've created an amine. Did I say animation? I think I did. I mean amination. That's a very, very tricky one. Like, I'm not animating anything. This isn't like Mickey Mouse. I am aminating things, though, because this is an amine. You get the subtle difference there? Yeah. You're tired today. Okay, so everyone appreciate that? Very exciting. Okay, what do we get from this? Is that what we got?
I got it.
Yep, this is what you should get. Okay, to the less substituted site should be a bond to the nitrogen of the secondary amine, where the carbonyl carbon was, where the carbonyl bond was, and a double bond on the less substituted side. Okay, so what we should get. Okay, so one thing you can do with this is you can actually alkylate the alpha site. Okay, so if I ran a reaction where I added CH3I and followed up with some H3O+, this is actually what's going to happen. I'm going to show the end of the CH3I, and then we can work through the second mechanism if we want. Okay, I will see that this can swing down and thus push out the pi electrons to serve, in essence, as a nucleophile. If you follow the resonance structure for this, you would find that this atom here is my nucleophilic atom. Okay? It's this alpha site that's my nucleophilic atom. Okay? So you see loss of a leaving group. This has to be SN2-like. Okay? It has to be SN2-like. As a matter of fact, I'm being very simplistic here. Really, we have different qualifications for this, and we'll talk about that in just a second. But in essence, this is what you get at the end of it. Okay? You've added a methyl group. So here is the methyl group that you added from methyl iodide, right? So this came from CH3I. Okay? But now you have a double bond. You're back to where you started from. You're back to that whole place way back when, right? That you needed something, you need to form an enamine, whatever, right? But we actually don't do that in this case, okay? Oftentimes when we use this to alkylate at the alpha site, what we do is we throw in some H3O+. What do you think is going to happen when I take this and I react it with H3O+? What happened to acetals when we added in H3O+? They went back to the aldehyde, because acetal is an aldehyde, but yes, so this is going to go back to the ketone, right? Can you see that mechanism in reverse? Yes, no, maybe so. So if you took that species there, you add H3O+, what's going to happen?
Just gonna go back to that.
Okay, the first step is to see maybe, or first thing you might want to do to see what might happen is to show the resonance structure. So the resonance structure of this looks like this. there's my resonance structure. So what do you think our first step might be here? Water attacks. Because what am I gunning for? Just like this reaction is all reversible. I took a ketone, I went to an enamine. If I'm in an enamine, what am I going to get in reverse? The ketone. Okay, yeah. Do I have an extra carbon? I'm so busy standing on my tippy toes.
To the very
the
right.
last one.
Yeah. That one.
Yeah.
Thank you. All right. So water is going to attack. We need to R this again, right? Is this first step reversible or irreversible?
Reversible.
And why is that? It's a neutral nucleophile. Is that what you're going with? It can go on, it can go off. Yeah.
So we can't show the nucleophile attacking before a resonance structure. We can't.
No, you can. No one was telling me what to do though, so I said, let's draw a resonance structure and maybe you'll see it. You saw it before. That's great. Speak up.
But I mean, would that be points taken
No,
off?
you would not get any points off if you show water attacking at this
Okay.
site over here. I just drew a resonance structure to get people to start thinking about what would happen. Absolutely not, Cassie. All right. So next step is, come on, this can get really boring unless we have some participation. Here we go. Deprotonation. Is this reversible or irreversible? Is this reversible? It's reversible. Why? Because you saw me draw it up? Yeah. How do you know if it's reversible or irreversible? I'm passing a proton from a protonated alcohol to a protonated water. Is there a difference in pKa really?
Not by much.
No. That's why the acid-base chemistry tells me it's reversible. So, okay. So now we are a third of the way there maybe. Maybe more. That would be exciting. Next step. I get down to something neutral and I always find something else to protonate, right? I'm back to something neutral. I got to find something new and novel to protonate. So what are my choices here?
The oxygen or
The nitrogen, because that would be the new and novel thing. If I protonate this alcohol, I'm doing exactly what I know can happen, right? Reversible. So I'm going to protonate the nitrogen. Reversible or irreversible?
Reversible.
Reversible. Okay? Good? Okay? I'm going to kick out my leaving group now. Absolutely reversible, because I'm kicking out a neutral nucleophile, and that neutral nucleophile can come back in. So that's absolutely reversible. So now I'm down to something. I've switched it on you. I hope that's okay. Moving this up. And last step, deprotonation. Okay. You can use the amine or water at this point. Truthfully, after the first couple of times, you have them all there anyway. Okay, does everyone see this? Yes? All right. Time check.
12:44.
12:44. Plenty of time to do the Wittig reaction. Okay. Are there any questions on this? Okay. So we have some trailing. Oh, actually, you know, it might be faster to do. We'll do the hydrogens. Okay. Change my mind. We have one last unit in here, and that's Wittig before we start trying to put it all together and try and see how you can use it in synthesis. But the last nucleophile, really, that follows similar patterns are the hydrogen nucleophiles. Now, this hydrogen nucleophile can be added with two different agents. You can add them with lithium aluminum hydride. Have you done these reactions in the lab? Do you use lithium or sodium borohydride? No? Neither of them? That's too bad. Okay.
Next week, isn't it?
So there's lithium aluminum hydride. So this is LiAlH4, and it's called lithium aluminum hydride. Have you all been following that plane getting lost over the Indian Ocean or whatever? Their latest theory is that they were carrying lithium batteries and they actually caught fire. Did you hear this? Yeah, because lithium's trouble, right? Lithium can ignite in very sort of water-saturated environments. Anyway, that's just a little tidbit of information. So lithium aluminum hydride, sodium borohydride is the other one. So you guys haven't, I mean, I know you talk about redox chemistry in bio, but you haven't really hit a pretty strong redox unit here in chemistry yet. It makes it a little bit harder to discuss this, but there is, in essence, a continuum of oxidizing agents and reducing agents, things that are stronger and things that are weaker, okay? And that is also true for reducing agents. Each of these is what we would call a reducing agent. Anytime you add hydrogen to a molecule, it's undergoing reduction, right? When you think about reduction, it should be removing oxygen, adding hydrogen. Those are two sort of concepts that will speak to a reduction mechanism that will be undergoing. So if we're adding hydrogen, of which these are hydrogen reagents, we are talking about reduction mechanisms, and we're talking about these as reducing agents. That's what they're called when they actually will do reduction on a given reaction, okay? So we're going to be reducing these ketones and aldehydes down to alcohols of some variety. Now, the difference between these two agents is how strong of a reducing agent they are, okay? And that really has to do with the ionic nature of these bonds. Now, they appear to be covalent bonds, and while I would agree they seem to be covalent bonds, any covalent bond can have what we call ionic character. And this bond here, between aluminum and the hydrogen, has more ionic character than the corresponding boron hydride bond, okay? That ionic character is derived, that concept is derived from knowing the differences in electronegativities, right? Most simplistically, when you learned about ionic and covalent bonds, you were told that if you subtract the electronegativities from one another, something 1.5 is greater is an ionic bond, right? And less than that is a covalent bond, and there is a passage between nonpolar covalent and polar covalent, right? So the differences in electronegativity are greater here between aluminum and hydrogen than they are between boron and hydrogen. Hence, this bond here has more ionic character. And what it really means is that it's first more reactive, but really what I would say is that it has a higher population of hydride in solution, okay? So there's more hydride available, and it's much more reactive, okay? So this is a reagent that you don't go to use unless you have to. You only use it when you have something that's reticent to react. You don't necessarily use it if sodium borohydride is good enough to do the reduction reaction that you want, okay? Now, remember last week I had that, or I guess it was earlier this week, we had that chart up on the board over here, and we were talking about how reactive these carbonyl compounds were, right? What I can tell you is that the aldehydes and ketones will react with either one of these, okay? Either one will react. Whereas when I get up to carboxylic acids, which are much less reactive, right? They were lower on my chart, much less reactive. Those molecules do not react with sodium borohydride, and we're forced to use lithium aluminum hydride there, okay? So my point in telling you about the two different types of reagents is we will see them both used on any exam material with aldehydes and ketones. But remember that only, and I will be reminding you, lithium aluminum hydride will react with the less reactive carbonyl species, okay? So this is the opposite of the oxidation reaction, so we'll just put this out and then we'll send you on your merry way. Aldehydes and and ketones, you know, will oxidize, or alcohols will oxidize to give you aldehydes and ketones, right? A primary alcohol will oxidize if I use PCC, so if I use permanganate, it would go all the way to a carboxylic acid, but it will oxidize to an aldehyde. I can also get reduction, and this is the new material, right? Lithium aluminum hydride or sodium borohydride. It's okay on an exam to just write these. Truthfully, they have workup. You need some water and acid, some sort of washout to get your neutral molecules out. So generally you see it as step 1, step 2, if you really follow the lab procedure along. But more often than not, especially out on the interwebs, you just see this. So we'll be fine if you just write lithium aluminum hydride, sodium borohydride. That's going to get me back from my aldehyde to my primary alcohol. And as you know, secondary alcohols get me, what do secondary alcohols get me? Ketones. And so if I reduce them with the same reagents, I'll get back to my secondary alcohols. What about tertiary alcohols? They don't react. Good job. Go. Fourth, have a great weekend. Should be nice on Sunday.